So I'm going to talk about complex world knowledge from simple linguistic input. And first, I want to acknowledge my collaborators, so Gabriel Grant, Francisco Pereira, and Fedorenko. So I'd like to talk to you about the relationship between language knowledge and world knowledge. And very generally, we can say that the linguistic units that we store in the lexicon are a system for communicating mental structures, right? We can use them and combine them together to transfer content from one mind to another. And today I'm going to focus on a specific subset of the lexicon. I'm going to focus on words, and not because words have some privileged status, but because words are a convenient place to start when looking at the relationship between language and world knowledge. And the computational model that I will use later is an off-the-shelf model that was trained on words, not on smaller or larger units. So we'd like to say that words are a system for communicating concepts broadly defined. So what are concepts? Well, they organize our knowledge of regularities in the world, right? They are generalizations about the kinds of things that exist and the properties that they have. And words, in turn, are associations between forms, auditory or visual, and abstract knowledge, such that differences between words correspond to distinctions between things. Now, you might think that this correspondence is not that simple. Maybe it looks more like that. So to make things simpler, I'm going to focus on a specific case, which is our knowledge of concrete nouns and their properties, which corresponds to, concrete objects and their properties, which corresponds to some nouns and adjectives. Now, just to make a quick note that in the view that I've been mentioning, words have sort of mapping to things, or words are labeled for things, and you might disagree with that, like Gary, and think maybe that words are cues to meaning and they don't have fixed meanings of their own. And so that differences between words teach us about distinction between things. There is some causal relationship of learning or inference. And I think whichever view you prefer is consistent with the work I'm going to show today. They're not mutually exclusive. One issue with this correspondence is that our world knowledge or semantic memory is very rich and detailed and complex, but word meanings or lexical semantics only capture a subset of that knowledge. So for example, the concept of dog includes its appearance, biological properties, behavioral tendencies, cultural roles, but the word dog maybe only captures a subset of that. And a famous example is the English word cousin that doesn't capture the sex or gender of that kin. And so any theory of lexical semantics should specify what subset of conceptual knowledge is captured by the lexicon, and the rest of that knowledge requires us to put linguistic units together productively. And to address this issue, I'm going to take a bottom-up approach that I'm going to sketch now. And so the overall question is how much of object knowledge can be derived from knowledge of words. And to make this interesting, I'll ask how much of complex object knowledge can be derived from simple knowledge of words. And I'm going to explicate what I mean by these terms. But the idea is how far in object knowledge can we get with relatively little knowledge of words? And specifically, I will focus on very simple kind of linguistic knowledge, which is the statistics of word co-occurrence in natural input. And we know that people track word co-occurrence statistics and they're sensitive to them during online language processing. And what I mean by simple is that co-occurrence statistics are very impoverished. They don't explicitly capture syntactic dependencies. We don't treat words as having internal structures. We don't use symbols or lambda calculus to represent meanings, and so on. And so the bottom-up approach that I just sketched can be summarized with this thought experiment, one of those that Gary mentioned. If a human only had access to word co-occurrences without other linguistic knowledge, without other non-linguistic knowledge, without innate representations, what kind of object knowledge would such a mind have? And of course, it's just a thought experiment, but we can have an empirical experiment and ask if a machine only had access to word co-occurrences, what kind of object knowledge would it have? And so when you train a machine learning algorithm on a huge corpus of word co-occurrences, and you ask that algorithm to derive word representations, you get something that's called a word embedding. The one that I use is called glove, but let me just quickly introduce word embeddings if you're not super familiar with them. So word embedding is just a high dimensional space where each word is a vector. Here I'm showing 3 dimensions of the glove word embedding just for visualization. It actually has 300. And here's the vector for the word man. Now the key characteristic of glove is that words that occur in similar contexts are represented by similar vectors that are close together in the space. So for example, here's the vector of woman, and they're both used in very similar contexts, so they're close together. So the critical idea here is that spatial proximity corresponds to similarity in patterns of linguistic use. So the dimensions themselves are uninterpretable. What matters is distance. And here are the vectors for actor and actress, which are farther away because they are used in slightly different contexts. Now, this space already has some structural properties that are interesting. For example, the path or trajectory from man to woman or from actor to actress has the same direction. And the same is true for waiter or waitress or duke, duchess, and so on. So you can see that this gender sort of direction is consistent in the space. But here's a problem. Distance in the space corresponds to similarity, but every two vectors only have one distance between them, only have one similarity. Whereas conceptual similarity they're very context dependent. So if you think in the context of wealth, for example, waiter and waitress should be close together, and king and queen should be similar to one another. But if now you think on the concept of gender, now waiter and king should be much closer together, and waiter and king, and then waitress and queen should be closer together. And so this seems to be a fundamental limitation of word embeddings. And so we wanted to ask whether context-dependent relationships between objects be derived from word embeddings, whether they are implicit there. And I'm going to show you a solution that we propose that's called semantic projection onto a feature subspace. And I'll use an example. So let's say we think about animals. Here are some vectors. And if you look at hawk and duck, they're pretty far in the space. But let's say we want to think about animals in the concept of size. Now duck and hawk should be very close together. People judge them to have very similar sizes. How would we extract that from the space? Well, we propose to take the vectors of the words small and large and connect them by a line. So they denote opposite ends of size. And when you connect them with a line, you get a one-dimensional subspace. That's what we call a feature subspace. You can think of this as a mental scale. And then we take the vectors of all the animals and we just project them on this line. That's what we mean by semantic projection. And when you project them on this line, what you get is that now duck and hawk are very close together. So to test whether this works, we used 52 categories and features. So for example, we projected animals on the line from small to large. We also ranked animals by danger, projecting them on the line from safe to dangerous, or on the line from dry to wet to look at habitat. And then we had weather phenomena by how dangerous they are, or weather phenomena by wetness. We had weather by heat on the line from cold to hot, states by heat, states by wealth from poor to rich, sports by danger, sports by wealth, and so on. And so we made sure our classes had animate and inanimate items, natural or man-made, common or proper nouns, and so on. We had between 30 and 50 items in each category. And we did the semantic projection, and to evaluate how good it was, we compared it to human judgments. So we took humans on Turk, we gave them, for example, a line from small and large, and we asked them to place animals. So they placed alligator, then they got another line, and they placed chicken, and so on. And so I'm going to show you now a comparison of human judgments and semantic projection. On the x-axis is human ratings of animals by size. On the y-axis is the semantic projection. So for example, mouse is judged to be very small by both, and mammoth is judged to be very large by both. Of course, this doesn't always work. So mosquito is judged to be medium-sized by semantic projection, but very small by humans. But overall, across animals, you see a very nice correlation with human ratings. So now I'll show you the same category animals, but different features. So you can project them on wetness on the line from dry to wet, and you get a nice correlation, or on the line from safe to dangerous, and again, you get a nice correlation. And importantly, we really extract here context-dependent similarities. The relationships are not all the same. So dolphin and tiger are close in size, but very far apart in wetness or far apart in danger. And I can also show you the same feature, danger, but different categories. So mythological creatures, angel and fairy are safe, sphinx is in the middle, demon and devil are dangerous, or cities in the world where Vienna and Venice are safe, Houston is in the middle, and Detroit and Baghdad are dangerous. To show you all the results, I'm going to show a matrix where rows are the categories and columns are the features, and I'm going to color the correlation between human judgments and our semantic projection. So everything colored is something we tried, everything in gray is pairings we didn't try, and the thick borders are significant results. So not everything is significant, but hopefully you can see that overall this works pretty well. And importantly, this works better than other methods like computing the distance to just one end, so computing the distance from animals just to the word big. It works better than PCA and so on. And importantly, it's robust to the removal of the most extreme category members. So it's not that this projection just recovers the biggest animals and the smallest animals. Even if you remove those, you still get correlation with human judgments. So what I wanted to show is that we can get context-dependent knowledge of concrete objects that is represented in word embeddings. And it's a domain general solution in the sense that it works across distinct object classes and properties. And what we like about the semantic projection is that it's geometrically explicit, unlike extracting knowledge with neural networks or from neural networks in ways that are less clear. It's a sub-symbolic model, unlike world knowledge represented with feature lists or structured schemata or intuitive theories. And it's trained on raw co-occurrences, unlike models that are trained on dependency parsers or supervised learning. And more generally, this is proof of principle for learnability of concepts without non-linguistic experience, which is, for example, consistent with the findings in congenitally blind individuals that Gary mentioned. So thank you.
Idan, a question. So the dimensions are provided by you, the experimenters. Right. Is there a way to automatically extract salient dimensions?
Great question.
To know that size is a dimension, that dangerousness is a dimension. Yeah.
So we don't know, but it's one of the questions we want to look at next. One thing you might imagine is that somehow antonyms end up very, very close in space, even though they're opposite, they're used in similar contexts. So maybe distance could be one clue, but we want to, that's one of the biggest questions. How do we know what makes a dimension? The other two questions is how do we know what makes a category? And how do we know which categories go with which dimensions? So there we think maybe the answer is variance, right? If you project a category on a dimension and you get very little variance, maybe that's not a good dimension for the category, but we haven't started exploring any of that yet.
Sorry to be quick to ask questions here, but you could imagine that, you know, anything could be a dimension, right? Like susceptibility to malaria, you know, or and wouldn't that be an interesting answer to that question? I mean, why do we have to think that there is some fixed set of dimensions? The very idea that you would be able to draw a dimension based on, you know, large, small, fierce, I don't know, whatever. I mean, it seems to capture the idea that we can flexibly you know, answer questions of this kind, right? And
I agree. I think it's really interesting. And it would be interesting to see how consistent different people are in their judgments when you get them weird dimensions, right? You can imagine a dimension from blue to open, and definitely some things are bluer than open, and some things are more open than blue, and some things just kind of meaningless with regard to that dimension. But yeah, I think it's really interesting to look at sort of less natural dimensions and see first, whether people agree with one another in those judgments, and if they do, does that correlate with what we get in such spaces?
So, I mean, some of the Barcelou dimensions might be a challenge for glove vectors, like things you would take with you when you were rushing out of your apartment because it was on fire. But
right.
It would be interesting to explore.
But maybe those would be, you know, maybe when you take something like BERT or GPT and you take the representation of that sentence and that's a line you project things on. I don't know. Sounds like
yeah, but that's a much different thing than just glove vector.
I agree. It has attention. It has all those weird things. We're also thinking of dimensions that are not binary, right? Like number of legs or color or something like that, right? How do you, that's not a line. That's a different kind of subspace. That's not one dimensional, and how would you represent that? So maybe you do PCA on those vectors and that's the subspace. I don't know.
Very interesting.